For years, deep learning models struggled with long sequences. Recurrent neural networks processed words one by one, making them slow and forgetful. We needed a better way to handle context.
Right, and we've talked about how attention helped RNNs focus on relevant parts of the input. But it was always an add-on, a helper. What changed to make attention the main event?
That's exactly the question. In 2017, a paper with an incredibly bold title dropped, "Attention is all you need." It proposed a radical shift in how we approach sequence processing.
It implies a simplicity, doesn't it? Like we don't need all that other complex machinery, just this one core idea.
Precisely. The paper introduced a new simple network architecture, the transformer. It's fundamentally different from what came before, streamlining the entire process.
Simple in what sense? Neural networks can get incredibly complex very quickly.
Simple, because it was built from the ground up to address the limitations of previous models. The key is it was dispensing with recurrence and convolutions entirely.
Wait, no RNNs or CNNs? Those were the workhorses for sequences. How can you process a sequence without some form of sequential processing or local feature extraction?
That's the core idea. The transformer is based solely on attention mechanisms. Instead of processing word by word, it looks at all words simultaneously to understand context.
So it's not just using attention as a helper. Attention is the only thing moving information around? That seems like a massive leap.
It is, and that leap had huge practical benefits. It resulted in models that are, quote, more parallelizable and requiring significantly less time to train. This changed the game for model scale.
Parallelization is critical for modern hardware, so faster training and better performance simultaneously. That's the holy grail, isn't it?
It truly was. For example, on machine translation, it achieves 28.4 BLU on the WMT 2014 English to German translation task, significantly outperforming previous state-of-the-art models.
Those are impressive numbers. So this isn't just a theoretical improvement, it's a measurable leap in capability for real-world tasks.
Exactly. But to really appreciate how it does this, we need to understand what this solely attention part means. How can attention build deep, contextual understanding without recurrence?
That's my biggest question. How does it work? I want to see how that simple network architecture actually pieces together.
Let's begin by looking at the model as a single black box. For machine translation, it takes a sentence in one language and outputs its translation. This is its external behavior.
Okay, that's familiar from many sequence-to-sequence models. Input on one side, output on the other. But how does it achieve that without the usual components?
Inside that black box, we find an encoding component, a decoding component, and connections between them. This high-level structure remains, but the internal mechanisms are new.
So it's still an encoder-decoder architecture, like the ones we've discussed before. That's a good anchor point. What do those components look like internally?
The encoding component is a stack of encoders. The paper used 6, but it's a hyperparameter. Each encoder refines the input, passing its representation up the stack.
A stack, so layers upon layers, each processing the output of the previous one. Does each layer do the same thing, or do they specialize?
Each encoder has 2 sublayers, a self-attention layer and a feed-forward neural network. These 2 components are where the magic happens for each word in the sequence.
Self-attention again. That's the core. And a feed-forward network, which is common in neural nets. How do these interact to process a word?
The self-attention layer helps the encoder look at other words in the input sentence as it encodes a specific word. Think of it as allowing a word to understand its context.
Like when I read a sentence, I don't just focus on one word. My brain constantly relates it to all the other words I've read. Self-attention does that for the model?
Precisely. And this is key for the transformer's efficiency. While self-attention creates dependencies to understand context, the feed-forward layer does not have those dependencies.
So the feed-forward part can be calculated independently for each word in parallel? That's where the speedup comes from, by decoupling those operations.
Yes, let's use an example. The animal didn't cross the street because it was too tired. What does it refer to here? A human knows immediately.
It refers to the animal. The street doesn't get tired, but a traditional computer would struggle with that ambiguity.
Exactly. When the model is processing the word it, self-attention allows it to associate it with animal. It learns these relationships directly from the data.
So instead of a hidden state evolving over time like in an RNN, each word essentially gets to query all other words for relevant information right then and there.
That's a fantastic way to put it. This querying is fundamental to self-attention. Now, let's dig into how that mechanism actually works with concrete vectors and operations.
Okay, the high-level picture makes sense. But how does a word look at or associate with another word computationally? What are the actual steps involved?
The first step in calculating self-attention is to create 3 vectors from each of the encoder's input vectors. These are called the query, key, and value vectors.
Q, K, and V. So each input word isn't just one vector anymore. It splits into 3 distinct representations?
Yes, they're created by multiplying the embedding by 3 matrices that we trained during the training process. These matrices learn to transform the word's meaning into specific roles.
So the Q, K, V are learned transformations, but what do query, key, and value actually represent conceptually?
Think of it like searching for books in a library. Your query is the search term you type. The key is the metadata on each book, title, author. The value is the book itself, the actual content.
That's a great analogy. So the query is what I'm looking for, the key is what I have that might match, and the value is the information I provide if there's a match.
Exactly. The second step is to calculate a score. For a given word, its query vector is compared against all other words' key vectors.
So if I'm word A, my query asks, how relevant are all other words, B, C, D, etc., to me, word A?
That relevance score is calculated by taking the dot product of the query vector with the key vector of the respective word. A higher dot product means more similarity and thus more relevance.
So if animal's key vector is very similar to its query vector, their dot product will be high, signifying a strong connection?
Yes, after getting all these raw scores, we divide the scores by 8, then pass the result through a softmax operation. This normalizes them into a probability distribution.
Softmax gives us weights that sum to 1, right? So now for each word, we have a set of weights telling us how much to attend to every other word in the sequence.
Precisely. The fifth step is to multiply each value vector by the softmax score. The intuition here is to keep intact the values of the words we want to focus on and drown out irrelevant words.
So if animal has a high softmax score for it, its value vector gets amplified. Irrelevant words get multiplied by tiny numbers, effectively disappearing from its context.
The final step is to sum up the weighted value vectors. This produces the output of the self-attention layer for that specific word's position, a new context-rich representation.
So for each word, its output vector is a weighted blend of the value vectors of all words, where the weights are determined by its query's similarity to other words' keys.
You've got it. This is the learned interpolation we talked about earlier. Every element in the input contributes to the new representation, with weights learned dynamically by the network.
That's elegant. It means the model doesn't just passively receive context, it actively queries for it. And this can all happen in parallel for every word all at once.
Exactly. This parallel processing capability is what made the transformer so revolutionary. And it led to incredible applications, like BERT, which we'll look at next.
Okay, so the transformer gives us contextually aware representations very efficiently. How did this lead to such a massive leap in language understanding like BERT?
The transformer's ability to process sequences bidirectionally and in parallel was a game changer. This led directly to models like BERT, pre-training of deep bidirectional transformers for language understanding.
So BERT is essentially a transformer, specifically leveraging its encoder part. And bidirectional is key here, isn't it?
Absolutely. BERT stands for Bidirectional Encoder Representations from Transformers. The bidirectional part means it considers context from both sides of a word simultaneously.
Which the self-attention mechanism naturally allows, because it's looking at all other words, left or right, at once to form its context.
Exactly. The paper states BERT is designed to jointly conditioning on both left and right context in all layers. This is a powerful form of contextual understanding.
Unlike previous models that might read left to right or combine two separate left to right and right to left passes, this is truly simultaneous.
That's the critical distinction. Unlike recent language representation models, BERT builds these deep bidirectional representations during pre-training on vast amounts of unlabeled text.
So it learns a very rich, general-purpose understanding of language structure and meaning before it's even asked to do a specific task.
And this pre-training makes it incredibly versatile. The pre-trained BERT model can be fine-tuned with just one additional output layer to create state-of-the-art models for many tasks.
So you don't have to build a whole new model architecture for question answering or sentiment analysis. You just add a tiny layer on top of a pre-trained BERT.
The impact was enormous. BERT achieved pushing the glue score to 80.5%, 7.7% absolute improvement, which was a significant leap on a benchmark for natural language understanding.
And this wasn't just on one specific task. GLUE is a collection of diverse tasks, proving its general language understanding capability. This shows the power of the pre-training.
Indeed, in previous episodes like #TCM153002, we touched on BERT's evolution. Today, we've seen how the transformer's mechanics, especially self-attention, made this leap possible.
It all clicks now. The parallel processing of the transformer's self-attention enabled deep bidirectional context, which was then leveraged by BERT for pre-training general language understanding.
Exactly. So when would you reach for this? Anytime you need robust contextual understanding of sequences, especially if parallel processing and deep pre-training are important.
I'm Maya. Thank you for thinking this through with us.
I'm Arjun. Another idea in 3 hours. Take care of your mind.